Thank you. Thank you, Ulrike. Thank you, Stefan. It's really a pleasure to be here. And it's for me, it's a delight being new to Vienna. This was one of the reasons I really thought I should come over from Basel, because there's a much larger community, of course. And so I'm really glad to be allowed to be already involved right away. I'll be telling you about things we've been doing, and hopefully this could be relevant for TACO too. In particular, as Georg mentioned, we are interested in this question of compound space. And actually, Björk yesterday, he mentioned a problem where the composition, the stoichiometry was not fixed, right? And so propagating, sampling different species, different stoichiometries can be relevant. Of course, not always, but sometimes. So there is a little retrospective I wrote last year with Kieron Berg on machine learning and chemistry or chemical discovery. And this has had quite a lot of attention and enthusiasm in the field. And there's the statistics we produced for that retrospective. And of course, some point any exponential growth will cease, but for the time being it's still has a lot of momentum. So my particular emphasis lies on what I like to call quantum machine learning, and hopefully I can explain to you a little bit more what that means. So it's before we enter into things, we should be careful in making the distinction to use of quantum algorithms and quantum computers for machine learning. And if you look this up on the wiki, you will find this little matrix. And so there are types of algorithms and types of data. And so we have quantum data, but we rather are working with classical machine learning algorithms. Now this notation is a little bit in following the convention in atomistic simulations, that whenever we study a quantum object, we like to use quantum as a prefix, right? Like in quantum Monte Carlo or quantum chemistry or quantum molecular dynamics, like ab initio molecular dynamics or first principle molecular dynamics. So that's the usual way we do this, and so I like to stick to that. I'd also like to use this acronym because I believe we are quite different from the more conventional quantitative structure property relationships, such as they are common in cheminformatics or bioinformatics. Right? So there's a long tradition of using machine learning in these fields, and we of course don't want to ignore that field, but we would like to go beyond and also tackle quantum problems. And basically we have the laws of physics on our side. So particular the electronic Schrödinger equation here with nuclear charges Z and coordinates R, which represents one of the bottlenecks in materials compute campaigns. The other property, which we study less, but I think is equally of interest and it's equally sound to look at this with machine learning, is it comes from statistical mechanics, and that's your Boltzmann average of some observable. Here's a pretty picture to whet your appetite. Here's a caption a student of mine prepared for a Nature Chemistry review with Alex Tkachenko and Klaus Müller that sort of illustrates the underlying idea. So suppose you have some compound, and this is actually aspirin. We omit all the hydrogens for clarity. So all the stars here are atoms from aspirin. And then superimposed on each atom, we superimposed much smaller another molecule that shares at least one atom, right? And so the argument is a little bit, so these are not completely independent species, right? They share some similarity, some rigorous similarity, and we'd like to exploit that, right? So one recent contribution with a postdoc of mine, Bing Wang, was to establish a sort of dictionary of small fragments which you can use to then stitch together to explore compound spaces of much larger compounds. And this little dictionary, the 1,000 smallest compounds you see here in this animation, they're just in a 10 by 10 by 10 matrix, and this is this animation, and we can actually look at them. So these are fragments relevant to organic chemistry. So A molecule like aspirin you could describe with this dictionary very well, right? In that paper we show how to do that. In this review we also discuss an approach where in a sort of cycle you could systematically converge towards materials that come closer and closer to target properties. So addressing the computational materials design or molecular design question is something that could be tackled with the methods we are trying to push forward here. If you are interested in more details, there was a chemical review, an entire issue devoted to machine learning and the chemical sciences. I co-edited this issue together with Michele Ceriotti and with Cecilia Clementi, and we were also allowed to contribute our view on this, so you can look up any references or more materials in this review or in the issue. So this is a little bit on the quantum machine learning, what I wanted to say in the introduction. But what about chemical compound space, right? So this is a little bit the application of machine learning consistent with the rules of quantum mechanics towards chemical compound space is really what's at the core of our interest. Now, the way I view compound space is as something inherently multiscale. We have the compositional degrees of freedom, so stoichiometries, we have constitutional degrees of freedoms, how the atoms are connected, what kind of bonding patterns, the graphs, and then of course you have all conformational degrees of freedom. And any such combination will result in a configuration of atoms that corresponds to a minimum in the free energy landscape, where we assume that the surrounding barriers are sufficiently high to prevent the system from spontaneously decomposing, right? And so to me, this is reminiscent actually of some fractal geometry. You can sort of construct graphs on these different levels, and every time you zoom in onto a lower scale, you will see the emergence of new physics, right? But there are similarities at the same time. So it's very intriguing. And I'd like to use this opportunity to ponder a little bit more on this. This is, of course, our alphabet from which we would construct any stoichiometries. But this is, and it just in 2019, it was 150 years, and there was even in the New Yorker very rarely discusses sciences and natural sciences. So this was a rare piece. But you know that, or you may know that there are alternatives to mapping the periodic table, and these are just some I find very pretty, and these are some more. And the question is really, what is the best arrangement of this, right? Could we extract some knowledge just by remapping it? And of course, that's not a new idea. Pettifor's number is really something that tries to do that. As you might know, it follows this line through the periodic table, and if you arrange atoms in this sequence, then some relevant property, for instance here, the formation enthalpy of these nitrides or carbides, which you show here, they become linear if you follow the order of Pettifor. Right, so this is a beautiful example, I think, of just rearranging your dimensions, and you have an immediate access to a structure property relationship, very low dimensional, of course, but still relevant. So there's a recent paper from Hardy Gross and Miguel Marquez where they just found a modified scale from data mining from Pettifor, right? Now, of course, compound space is higher dimensional in general, and so the question is really, the more general question is, given a bunch of particles, a bunch of protons, how many stoichiometries could you realize, right? So there's a trick question I have. Somebody gave you 40 protons. Björk, how many compounds, how many stoichiometries could you make with them? What's your guess? 10 to 100, okay. Here are some examples, right? These are already 8 examples, 40 protons. If you pile them up all in one atom, you'd have zirconium, right? So there are many more. Would you like to revisit your estimate?
Yeah, but now we scale it down.
To 8? There are more.
No, to 10. 1,000.
1,000, okay. So this is a discrete number theory, right? How many integer partitions could you make from a given total number of protons? The number of ways to write NP as a sum of positive integers. And there's actually an illustration. It's called the Young-Ferrers diagrams. And here's the answer. You can have over 37,000 different stoichiometries. And this is how the number of stoichiometries grows with the number of protons in your system. So 37,000 is up here. On the way towards that, you can make these diagrams, and I filled up the easiest, and becomes immediately obvious, right, what this means. Right? And this is just the stoichiometry. This is not yet any bonding and no conformations. Right? So you can do this for every element in the periodic table here, and the number grows correspondingly, and I discussed this in the review in 2013. So for 10 protons, you see you have many common small molecules. They would all share that total number of protons. And if you presume charge neutrality, of course, that's also the number of electrons. Right? So all these systems have the same number of electrons. Quite recently, there was a study that used something very similar to that. It looked at different binaries as a function of number of certain species. So one species has index m, the other n, and it looked for stability islands in here, right? And this is actually a paper by Artem Organov from 2019, and he looked at all these silicate clusters. And the isoprotonic case, so what I just discussed with the partition theorem, this would be just a diagonal line on such a diagram, right? Then we come to topology, right? And you are probably aware that the number of graphs with the number of vertices you add grows combinatorially as well, right? This is just going up to 7 atoms here. And then after that, you can have some examples, and this is a data set, the QM9 data set, which we published. It has a subset. This is the number of, the subset of the largest number of constitutional isomers in QM9. The sum formula is C7O2H10. And you have roughly 6,000 of these molecules, and we did DFT calculations for all of them in QM9, and if you order them just in ascending order, then it looks like this, right? Now this is not a normal distribution, and note that every compound here is a different graph. So on each of these dots, you would have all possible conformations still, right? So this is all the same stoichiometry, and you can also see the energy density here. This is in kcal per mole, so in 1 kcal per mole, so roughly 50 milliV, you have something like 100 compounds, right? And so this is really, I think it illustrates a little bit how rich the space is. Now it's quite rich in this high density region, but of course as you go up here, there's nobody, right? Or you can't go further down here either, right? For that given stoichiometry, that's the end, right? So I think it's very fascinating. Of course, the carbon allotropes are another example of just differences in binding. And then the third scale or level is conformations, and the infamous Leventhal paradox, or David Wales, Leonard Jones clusters, and many people have studied this, of course. This comes from all the possible conformations. And so if you put all of this together, this comes from a paper of David Barreton and Waitao Yang. They sort of propose this representative set of molecules that are supposed to cover all of chemical compound space. In other communities, you have this Nature Insight from 2014 and 2017. Sorry, 2004 and 2017. There's this number of 10 to the 60, right, in terms of possible number of molecules. And these are just medium-sized organic molecules. So with what I said before, I hope it's clear why this number shouldn't be so surprising, right? That it can be that large. Now, in this 2017 review, this graphic was put here, and so 10 to the 60 is this bar. This is the atoms in the solar system, and these are data sets which we have studied so far. So I'd like to argue that this space is really fascinating, and I haven't understood it, much of it, but in terms of quantum mechanics, it's actually quite straightforward to define it. And I put here the Cohen-Sham equation for just one particle, most of you will be familiar with this. And in the Cohen-Sham potential, we have our external potential, and this external potential encodes explicitly the nuclear charges and the coordinates. And that's really what's varying, right? Now, the number of electrons is, of course, an additional dimension, but that's just one dimension. Here we have, so we have really 4n, if you wish, the coordinates and the nuclear charges. So in this coordinate system, then any compound would be a point, right? And so we would try to learn in this space properties, right? Now we can do this, and here's a graph from one of our papers where we present here the electronic energy. So we remove the nuclear repulsion, which I find quite it's not disturbing, but it's obfuscating, right? So the electronic energy is the hard part, and as a function of interatomic distance, it decays systematically. And as you change the nuclear charges in this isoelectronic series here, you see it has this shape, and it's quite smooth. And we can actually, for fractional nuclear charges, we can also solve the electronic Schrödinger equation. That, of course, has no correspondence to reality, but it means that we can construct theoretical gradients, and we can do these theoretical, call them alchemical perturbations. So in my lab, we really try to exploit both. We try to extrapolate here using perturbation theory, and to interpolate using regressors, right? So to me, these are two sides of the same coin, and in this perturbation theory, these are alchemical expansions, and they actually have a long tradition. It's few people doing it, but for a long time now, and then more recently, we've also started the machine learning methods. So for instance, in perturbation theory, you could calculate the perturbed electron densities of N2 along this blue line. So your perturbing Hamiltonian would interpolate N2 to the Hamiltonian of CO or BF, right? And now you have the densities to first, second, third, and fourth order, and when you pile them up, you recover CO and BF to a degree that it becomes indistinguishable from the SCF solution of those species. This was used for things that might be relevant to TACO, and this is a paper with John Keefe, which we published a couple of years back, where he tried to estimate the binding energy of adsorbents on surfaces, right? Using this alchemical prediction, and here you see scatter plots of the actual binding energy versus the alchemically predicted one. Now, these were due to SCF calculations, and these were due to perturbation estimates, which were for free, basically. And you see quite a decent correlation here for various adsorbents and surface and skin on platinum, palladium or nickel slabs. More recently, Batista also wrote a nice review in Chemical Reviews on catalysts and inverse design, mentioning machine learning as well as alchemy. And there's also this review in the International Journal of Quantum Chemistry on also by John Keefe and John Kitchen, both from Pittsburgh. Now, more recently, and I'm really excited about this, which is why I injected this in this talk, with a postdoc of mine, we discovered a symmetry in this chemical compound space. And I'd like to just very briefly tell you about that. Maybe this will also be relevant to surfaces. If you think about going from N2 to CO, obviously this must be symmetric, so CO is the same as OC, and that's due to the rotational symmetry. But it turns out when there's no rotational symmetry, you can actually also profit from a symmetry. And that's shown, you need slightly more complex systems, and it's shown here for this benzene molecule. So this benzene molecule when you mutate it to B, N, and B, it has a very similar electronic energy as this one with N, B, B, N. Right? And we call this an alchemical chirality because there's no rotation or translation how you can superimpose these two species. And you can see from benzene the perturbed electron densities, they are shown here for second and third order. And they only, in second order, they differ by sign. And in third order, they are identical again. And this results in the energy difference from benzene to these two guys to be degenerate up to third order. So to a very good degree, they are degenerate in the electronic energy, and then the nuclear repulsion is trivial to obtain, and you can rank then the energies of these guys without actually having to do any SDF for them. And you can do this for many possible dopants. And in this paper here, we demonstrated this for these anthracene derivatives. So we did over 2,000 with expensive quantum chemistry reference calculations. And then for this piscine, we scanned 400 million, more than 400 million derivatives of various stoichiometries, you can see here. And we can rank them by energy and then look how various features or descriptors in the compound change as you go up with your energy. And so we identified for each stoichiometry the least stable and the most stable. And all of this was done at virtually no computational cost, right? So we had to do the perturbations on the unperturbed piscine, and then you get 400 million compounds estimates on their ranking. So with this, I'd like to tell you now about the machine learning. In 2011, I organized a workshop at the Institute of Pure and Applied Mathematics on navigating chemical compound space. And this took place, this was at UCLA, and participants included Klaus-Robert Müller from TU Berlin, who was the chair on machine learning, Alex Tkachenko, an old collaborator and friend of mine, and Matthias Rupp, who was a postdoc with Klaus, right? And so we asked this question, how can we interpolate in chemical compound space? So each compound is a point in the space, and then Klaus suggested we simply use a kernel-rich regression model that looks something like this. The sum of our training instances for your query material M, you basically expand the property in training instances I, and every training instance gets a coefficient, a regression weight, which carries the units of the property, and it gets scaled with the similarity of query to training instance, okay? So it's super simple. You can get just a linear regression in this kernel space, so you can get regression coefficients just by inverting the kernel matrix of your training instances. So Björk also alluded to these models, right? They also result from Gaussian process regression. So it's one of the, maybe the simplest machine learning model you can think of. Now, in 2011, we then saw that using this as a representation for your molecule, this is a simple atom-by-atom matrix, which we call the Coulomb matrix. On the off-diagonal elements, we report the nuclear repulsion between the atoms. This kind of matrix is unique for any compound in the sense that you will not find two different compounds that have the same matrix. So you can use this as a representation of your material, and using this, Matthias Rupp generated the learning curves. So here's the error of the atomization energy on organic molecules as a function of the training set size, right? Of course, this error is measured on test molecules, not part of training. And after 5,000 molecules or so, we reach 10K cal/mole, which is roughly what a GGA would give you. But of course, such a query prediction would only require milliseconds. Right? This then got me into this game, and Kieron Berg was also a participant at this workshop. He also published a paper with Klaus Müller on learning density functioners. And I think this is important because if you recall the errors we typically make when using force field, semi-empirical methods, mean field methods such as Hartree-Fock, MP2 or QMC, this error comes down, but we also have to pay with the cost, right? And so this was always the trade-off. But if you had an extremely good approximation, of course, you could lower this, right? And that would be very valuable to the community. But what machine learning is promising is that we could replace this axis here by the training set size, which has to be acquired just once, and then you train a model. And so it's not a free lunch. We just shift the cost up front. But then once you have that, right, you can make the test predictions at negligible overhead, at the accuracy that was promised by your training set size, right? And so this, I think, is really why these machine learning techniques are so promising. Now, Vapnik is one of the fathers of the statistical learning, and he actually demonstrated or proved with others that on logarithmic, on log-log scales, you must observe such a linear behavior of the prediction error. This comes from the error going inversely with the training set size. This is the leading error term here. So if you do things properly, you really must obtain these linear learning curves. And so over the last couple of years, a lot of our work has dealt with the question, how can we improve these learning curves? Right? So the better these learning curves, the better your machine learning model, in short. Now, we looked at various ingredients of these models, and they include the question of the representation, the inclusion of legacy methods, and also how you select your training set. I'll skip very quickly through this. Basically, I have a couple of slides where on QM9, over the years, more and more representations have been developed and tested, always on the same data and on the same property. So it's a fair sort of comparison. It has become a benchmark data set, and I'll skip forward to 10 years or so of recent, no, less, 6 years of recent progress that was made from various groups around the world on the atomization energy of QM9, and you see that some of the best models will reach chemical accuracy, so 1 kcal per mole. This is typically the experimental uncertainty in thermochemistry experiments, right? This is where this number comes from. So that's 50 milliV or so. You need slightly more than 1,000 training instances. So to reach such an accuracy with coupled clusters is very, very difficult and costly, right? And here, after training on just 1,000 instances, you might be able to get there. Now, we are really interested in pushing this further. What are the limits on this? Our understanding is very poor on what limits these learning curves. And so these professors here agreed to pay $100 to anybody who comes up with a model going through this point, right? So reaching chemical accuracy at 100 training instances. So if anybody among the young PhD students feels motivated by that, please come talk to me. I can give you more details. What I wanted to mention today, though, are these legacy methods. I think they might be in practice extremely useful for getting immediately something out of this. And the idea is quite simple. Rather than producing a training set, very expensive methods, we could ask, well, if we also have cheaper results, more proximate, couldn't we just learn the difference between the two? So learning a correction, right? And this is, has become known as the delta method. Raghu Ramakrishnan from my lab and we have been developing this when he was in Basel. He's now a professor back in India. The idea is written here again. We have a correction, and this correction term from a baseline to a target system. And note also that the coordinates do not have to be the same, right? The machine learning correction can take care also of differences in coordinates. So basically learning this black arrow here, this correction, this is a possibility. And here's just one figure from that paper. What you see here is always the same target, G4 and B2, where we try to get to on QM9 data. And you see as a lower index the baseline method. And very encouragingly, so in green you see direct learning. And then if we use PM7 in orange or in red here, you see that we have a baseline, so we get an improved learning curve. And then if you go to PBE, you have a further improvement, that's in blue. And if you go to a hybrid functional, you get an even further improvement. So in some sense, the hierarchies of these baseline methods is reflected in the offset of these learning curves. We could also learn the differences between Hartree-Fock and coupled cluster, and this all works very nice. In this paper, More recently, we used this idea to learn van der Waals correction and non-covalent interaction correction for scan. And also here, we had a trick how to do this for very small data sets. So we basically used the S66, and we went up to 65 molecules for training and then tested on the remaining. But we could do this 66 times by reshuffling the test and the training. And so you get some statistics here and learning curves. And you see for various functionals here, you get different offsets. And for scan, you get a very competitive offset. And so we're stuck with scan, and we compare this to scan and D3. And here you see errors with green and red versus the error of scan in yellow. Now, of course, the comparison to D3 is a little bit unfair, because we could always, if we had more training data, we could improve the correction even further, right? But already at a very modest training set size, we can be as good as D3. And we can even extract some C6 coefficients from the predictions, which are reasonable, or many body contributions to the predictions, as well as atomic indices, where the van der Waals interaction is strongest. And here you see the systematic decrease in error in the binding curve for scan and D3, and for the machine learning correction over all the S66 scan. Now, this idea was just recently used by my collaborator, John Keefe, independent of me, to correct the alchemical first order prediction to make it more accurate. Okay? For the adsorption of these different species here on surfaces, and you see here in black the alchemical prediction, the training directly on the binding energy, and in blue you see, in red you see the delta machine learning model if you use the alchemical prediction as a baseline. So with this, I'm coming to the end. I try to do some outreach for students and collaborators on YouTube. We have this recent book in the Springer Lecture Notes in Physics, so with many chapters by people working in the field. We do most of our developments in this QML code on the GitHub. You're welcome to share or contribute. I'm also an editor-in-chief on a new journal by the Institute of Physics in the UK called Machine Learning, Science and Technology. So whenever you have results or new models that are sort of relevant to physics, but not necessarily to pure machine learning, then please consider this journal. It's open access. Finally, I'd like to still say a word on the sharing in the community. So most of us share the models either on GitHub or in the SIs. We put the data in various journals or repositories like Zendo or Materials Cloud. There are various workflows out there already, but we felt that one thing is sort of missing, and so we recently launched a new effort. This is a web server called lirolite.com, and you can actually query this page for compounds. So you can enter your favorite compound here. It will auto-complete the name. I don't know how they do it. It's amazing to me. You can upload coordinates as well, or you can even draw the graph. And then when you hit search, it will spit out something like this, including a 3D structure, which it predicts, and you can download this, or you can share the URL with your colleagues if you want to look at the same molecule or whatever. And there are various properties which we plan to expand on in the future. But most importantly, what we are looking forward is to include models. If you have a model which you would like people to use through a web server, then come and talk to us. We'd be happy to include it. So this is the team. Various people have contributed. We have had funding from the ERC, and this is the Institute of Pure and Applied Mathematics. And with this, I'm done, and I'd like to thank you for your attention.
Thank you, Anatole, for this beautiful overview talk. Are there any questions or comments? Let me start this. So you show that that you have these log-log learning curves that seem to be completely general. On the other hand, if you learn for solids, it seems to be the case that most actually all the papers that you look at, if you learn, say, interatomic forces for one specific material, it seems to level off at the level of typically, say 2-3 millielectron volt per atom. Do you have any insight why this works so well for molecules and seems to be more difficult for solids?
No, so we do have, we did a machine learning paper back in 2016 with Ricard Amiento on machine learning formation energies in quaternary crystals in the El Paso light class, where we observed the same learning rate. So I don't think it's solids versus molecules. I think it's rather when you go to a different property like the forces, you might have a higher numerical noise.
So it's ground state versus kind of
yes, and we actually
temperature.
We have one data set where first this was Alex group and together with Klaus Müller, they generated with default settings forces for molecular dynamics run on isomers, and we saw our learning curves level off like you just described. And then we went back, we rerun all these calculations with tighter settings, and sure enough, now our learning curves go much lower on the same atomic configurations, right? So it was really just the settings of the quantum code in the reference data.
Yeah, I would say 2 millielectron volt per atom is way beyond the errors that we have. Okay, but that certainly would warrant further investigation why we have this difference. So it could be on the energies,
it could be
ground
this
state energies versus excited states with forces.
Another possibility could be the representation,
sure.
If it's not unique, right? That's also something you see. For non-unique representations, you observe some leveling off it.
Yes.
Yeah. So
any other questions, comments?
Hi, very nice talk. Maybe I'm ignorant, but what's alchemical perturbation DFT and why is it alchemical? What's
okay, so I'm
here?
sorry, I skipped a lot of this, and I'm really sorry for the jargon. So what we mean really is maybe best shown by this, right? You can ask yourself, what happens if you go from N2 to CO, right? And what you can do is simply take the nuclear charges in your electronic Hamiltonian of N2, right? It's 7 and 7, and then you slowly vary them towards 6 and 8, right? And that's what we mean by Alchemica. So computational alchemy, it's a term, it's quite old actually, right? It's a bit ironic, but it has been for many decades. So, yeah.
Thank you.
Hi. I have a question regarding the non-covalent interactions that you are learning. I didn't quite understand what's the idea, because you said you're learning the difference between scan and some other functional, but usually adding non-covalent interactions is maybe not the bottleneck in an ab initio calculation. So how do you actually aim at describing what features of the non-covalent interactions do you describe, and how do you learn maybe in a bit more detail?
Thank you. So yes, our comparison to scan plus D3 would suggest what you're saying, right? But I would actually object to that statement. I think if you want to rigorously, so the training set we used was this S66 data set, right? And those energies were obtained with coupled clusters, single, double perturbative triples with a very large basis set. If you run this with Hartree-Fock, there's no binding, right? So you actually spend a disordinate amount of time if you want to capture these in general, right? It could be that for certain circumstances you don't need to, and D3 is enough, but I don't think that's generally true, right?
But do you use in order to capture?
Let me repeat the question. Do you use three-body descriptors and three-body terms?
Yes, so in the results I presented, we did use what's known as the FCHL representation, which does include, it's a systematic expansion, you can go up to any order. We went up to the third order. The Coulomb matrix, for instance, is a complete matrix, right? It would account for all higher order terms, right? So there's a little bit an interplay. You have to check with your representation if it captures that. I agree. Thank you.
Uli.
Yeah, Very interesting, thank you. So my question as an experimentalist, of course, is where do experimental data come in, right? And I can see for molecules you have a very, very accurate data set. And that maybe also goes to the same question as Georg has, like which data set do you get experimental one, not comparing to different levels of theory for experiments, for solids, and then for all these other things that we've heard about this morning, nanostructures, surfaces, those things. So how do you see going that way?
So this is why I wanted to mention this delta learning. I think this would be super exciting if we could say you have, let's say, DFT as a baseline, and then you learn the difference to an experiment on the same system, right? And this could allow you to really require much fewer experimental data points, right? To reach reasonable predictive power. So suppose this pink line would be what you would need if you had no DFT and just learning the experiment. And then with DFT, you might be able to push it in, and you reach the level of accuracy you need to meaningfully explore other ones and to make educated guesses on what to measure next, right? But that, I think that's very much a possibility. Yeah. Thank you.
Any other questions? I mean, first of all, €100 for learning from just 100 structures, that's cheap.
But from each professor, right?
Yeah, but it's just 20 professors, so it's
you're
still
welcome to join and pitch in more.
Yeah. Yeah. I think, I would keep
agree.
it to myself and not offer it to the public. Maybe one last question. I mean, you showed this hilarious number of combinations that you can have. Do you believe it makes sense to try to develop something like an universal force field that would work for a substitute for solving the Schrödinger equation?
I don't know. I think the answer will be, unfortunately, it depends. Right? So
sure.
We have...
Well, universal means it works for everything, right? For
yes,
any combination.
And that's appealing, right? But
yes.
we also know in these learning curves, and so this is, we are preparing a couple of papers right now for submission where we actually exploited the selection. And if you're willing to compromise by saying, okay, I need less universality, all your learning curves become much lower and better, right? But then, of course, you sacrifice that universality. So that's the trade-off, right?
Okay. Thank you, Anatole.
Thank you.
Yeah, let's thank the speaker again for his contribution, and we move on to the